Hi, my name is Nika Aromi, and this is Lab 3, where we look at the magnetic field of a bar magnet. The purpose of this lab is to understand the correlation between magnetic field and distance and understand the Biot-Savart law. We also want to compare experimental and theoretical values relating to magnetic fields and understand the discrepancy. In our results, we see that magnetic field when measured on axis is twice as large in magnitude than when measured perpendicularly. The fundamental physics principles at hand are mostly the Biot-Savart law, where we have a formula for when we have a dipole on axis, and we can solve normally for any situation with the formula on the right using the integral, using the constant for magnetic field times current times the cross product between the line segment and the r hat divided by the distance squared, as well as using right hand rule to get the the direction of the moment. Our system was the magnometer on the phone, our surroundings were the Earth and bar magnet, and our initial conditions were that the magnetic field in the x-axis was 0t, 0 Tesla, leaving only magnetic field in the y and z-axis. We assume there are no other magnetic fields except those caused by the Earth and the bar magnet. Before collecting data, we also found the magnet sensor on the phone so that we know that the data we're getting is true to the magnet sensor. We found where Bx was 20, 70, 120, 170, and 220 Tesla, and we did this by adjusting the perpendicular distance the magnometer was to the bar magnet, and we found that the closer we got, the greater the magnitude of the magnetic field was. And when we did it on a perpendicular axis, we found that we had to account for by correcting for by of Earth, and that our B net was 5.22 e to the negative 5 Tesla, and our by was generally a little bit bigger than the other two. In our results, we got this lovely graph where we have ln of bx versus ln of r, where we see the relationship between the x component of the magnetic field and distance, and we see that there's a linear regression there. In order to find mu for the calculations, we use the y-intercept of negative 14.23, raised e to that number, and we said b bar equal to b dipole, and we solved for mu. In our glow script code, we set up mu mag and then put all of our known values into the B formula in order to find the magnetic field the bar magnet was causing, as well as finding the perpendicular components of each one as well. We found that the magnitude of B at 45 degrees is 2.8 e to the negative 5 Tesla, which again is a little bit off from what we found experimentally. Some possibilities for error could have been that there was a lot of humidity, which there was a lot that day, it was raining, or there were other devices in the area that could have influenced the magnetic field being measured by the magnometer, which is also true any presence of metals, and there were like phones and iPads around which could have contributed to the magnetic field being off in our calculations. We also found that our computational model was 2 times less than that of our experimental, but because of all the errors present, our computational model is probably more accurate, and also it's not likely that our only magnetic fields present are from the bar magnet and from the Earth. Now, what if you hadn't oriented your experiment to compensate for magnetic north, and instead you laid out mirrors at an intermediate angle with respect to Earth's magnetic field? Our results would have been extremely inaccurate because we wouldn't have known exactly how much of the magnetic field in the X, Y, and Z component was coming from the bar magnet and what was coming from Earth. By setting our orientation to the approximate north-south axis, we know that our x-axis is 0, so any other value we get when we bring the bar magnet close is only due to the bar magnet and not due to the magnetic field of Earth. If we were to stick 2 identical magnets together end to end and run the experiment again, we would expect the direction of magnetic field to be the same, except the magnitude would be twice as much. And our conclusions are that bar magnets can be perceived as a magnetic dipole and As you get closer to a magnet, you experience greater magnetic field. Thank you so much.